Hello everybody, my name is Connor Thompson. This is my Physics 2212 Lab 3 report. This lab is a circuit-based lab that analyzes electrical concepts correlating with Ohm's law, such as voltage, current, and resistance, and how these concepts relate to physical components like capacitors, resistors, and observable phenomena like capacitor discharge. A circuit was designed with resistors of different values, 4700 ohms for the first one, and then we had a light bulb and a capacitor for the second one. Our lab primarily dealt with Ohm's law, which is V equals IR, the node rule, and the loop rule. And our design circuit would be the system. The surroundings could be any outside influence, such as air. Our main result was that I1 and I2 for the first circuit was about 20.41 milliamperes. The 47 ohm resistor had 0.953 volts. The 100 ohm resistor was about 2.03 volts, and the charging time was 1.8 seconds for the second circuit. The discharge time was about 18.19 seconds. Our results, this was our second circuit, which is the batteries, the light bulb, and the capacitor. This is our first circuit, which has like the multimeter here. The two resistors were right here. You can kind of see them here. And this is the chart for the second circuit that shows how the current kind of, well, this is like the shows how this current kind of decreases over time for the resistors. This is for the first circuit. My bad. Second kind of section of results is just all like the calculations that we did, all the values that we calculated throughout the lab, such as like I1, I2, the resistor difference in potential, all sorts of stuff that we'll get into later. Background of the experiment, our circuit initially has some charge and current flowing through it on account of the battery. The first circuit was designed with two batteries, a 47 ohm resistor and 100 ohm resistor. Multimeter probes were placed before the resistors to determine I1 and I2, which were both roughly 20.42 milliamperes. The voltage of each resistor was calculated as 0.953 for the 47 ohm resistor and 2.03 volts for the 100 ohm resistor by measuring the difference in potential. And upon changing the top ammeter right here to a voltmeter, the voltage at the top was 0 volts, and we recognized that if it were to have switched to the bottom ammeter, it also would have been 0 volts. The second circuit was designed with two batteries, a capacitor, and a light bulb, and we disconnected the battery to charge the capacitor, and then upon disconnecting the battery, we further determined that the time for the light bulb to turn off completely as the discharge time for the capacitor when there was no more energy in it. Our overall results were I1, I2 right here. Reverse, this was this. The battery voltage for the first battery and the second battery were both negative 1.5 volts. The difference in potential voltage here for 47 ohm resistor was 0.953, 2.03 for 100 ohms. The sum of voltage is negative 0.017 volts, and it ideally should be 0 volts because of the loop rule, but the fact that we got this it shows how close we were to getting the ideal value. Ammeter voltmeter was 0 volts as described in the previous slide. Charging time was 1.8 seconds. Discharge time was 18.19 seconds. The graph breakdown right here for the first circuit. The ammeter readings do not change. Low resistance the ammeter, and as such, the current is not affected as it flows through. However, the voltmeter is high resistance and does alter the current. But overall, the idea of increased resistance impacting current is shown in this graph because you can see current rises immensely as it gains charge and dies, but decreases with each resistor it passes through because it impacts the flow of the current. Um, that's just another kind of screenshot of the 18.19 seconds discharge, like one of the big results we got. Though we have assumed no charge could be lost as heat to the air and wires, this may explain any observable oddities in certain values because these do in fact happen. And as such, any errors caused during this experiment could likely be due to aspects such as the decreasing battery charge over time, faulty components like burned out light bulbs and whatnot, and charge loss in the environment. As for what if we had a capacitor with no resistor in the circuit in this ideal situation? What would happen? Well, the capacitor would charge much, much faster, maybe near instantly than as observed in the experiment because the current would flow directly into the capacitor without being impeded by a resistor. However, this would not happen in real life as batteries, ammeters, and wires all have some small form of resistance that impedes the flow of current, ultimately slowing the charging time. And even then, most circuits that you will see in real life will always have a resistor because it's a necessity to prevent electrical components from being damaged by an overflow of current. So this ideal situation would likely not happen. Even then, the measured time that we saw was much larger than predicted, and it took several seconds still, likely on account of all these resistant factors, such as the batteries and wires that still have some small form of resistance. Um, as described earlier, any error sources could be the charge of the battery. We had our batteries had to be replaced by our TA because they lost charge. Potentially old and damaged capacitors, resistors, burned out light bulbs, inaccurate multimeter due to low battery as well because that also runs off batteries and a charge lost in the environment via air or heat. And overall, this experiment was very interesting in showing how current behavior can be observed in a circuit, how it can be impacted by capacitors and resistors. And it was also interesting to observe how capacitors can store charge long after a battery has been disconnected, and how it can continue to supply this charge to other components like light bulbs. Anyways, thank you for watching. This was my Lab 3 report.